In 2016, astronomers looking deep into the cosmos witnessed a giant star detonate at the end of its life. But this star, named SN Requiem, did something completely unexpected. It exploded 3 separate times. Now, scientists at the Max Planck Institute have calculated that the same star is going to erupt yet again, sometime between 2026 and 2027. But stars do not die 4 times. The supernova only happened once. What telescopes are capturing is actually an immense optical illusion. Sitting directly between Earth and the shattered star is an enormous cluster of galaxies, acting as a massive cosmic barricade. By heavily distorting the dead star's light, this galaxy cluster has inadvertently formed a natural stopwatch, and researchers are using that stopwatch to solve the most persistent dispute in modern physics. The sheer mass of this galaxy cluster physically bends space-time into a deep well. When supernova light hits it, gravity acts like a lens, forcing the flash to split along distinct curved routes. Because these routes curve at varying angles, they are completely different lengths. Light travels at a constant speed, so a longer physical path means a longer journey. As a result, the exact same flash of light arrives at our telescopes months, or in this case, years apart. By tracking the exact time delay between flashes and measuring the geometry of the light paths, researchers calculate the absolute distance to the supernova. And once you have that distance, you can precisely measure the scale of the universe itself. That scale is exactly what astronomers have been arguing over for more than a decade. We know the universe is expanding, but our 2 most advanced methods for calculating the speed of that expansion, known as the Hubble Constant, are returning contradictory answers. Astronomers measure outward from the Milky Way using pulsing stars, calculating an expansion rate of 73 kilometers per second per megaparsec. Conversely, cosmologists measure inward from the edge of the observable universe using Big Bang acoustic ripples, arriving at 67. Both teams have refined their calculations to a precision of about 1%. The numbers should overlap, but they don't, and the gap is too large to write off as a simple calculation error. Each approach has technical vulnerabilities. The pulsing stars used by astronomers can be obscured by cosmic dust, skewing their apparent distance. Meanwhile, the afterglow calculations require researchers to bake in specific assumptions about invisible forces, like dark matter and dark energy. This decade-long gap leaves physics at an impasse. Either an unseen bias is corrupting traditional telescope measurements, or our foundational model for how the universe works is missing a piece. To break the tie, researchers are turning to a technique called time delay cosmography. This method completely ignores the messy chemistry of exploding stars and the heavy theoretical assumptions about dark energy. It relies entirely on pure, straightforward geometry. By recording the years-long delay between the repeated flashes of a supernova and carefully weighing the galaxy cluster acting as the lens, astronomers can triangulate the exact physical distance to the event. They then combine that distance with how quickly the galaxy is moving away from us, which is revealed by the stretch or redshift of its light. The result is a highly precise third measurement of the universe's expansion rate. Because time delay geometry doesn't rely on the chemical and theoretical assumptions that burden the other methods, it offers a clean slate. It is the only tool capable of definitively proving which side of the physics debate has the math wrong. Right now, astronomers are actively checking the sky, waiting to catch SN Requiem's 4th flash. A global team synthesized 7 independent mass models of the cluster, narrowing the supernova's expected arrival down to a tight window in either 2026 or 2027. The exact timing will dictate the answer. If the light arrives early, in 2026, the geometry will yield a higher expansion rate, validating the traditional astronomers. If the light takes a longer path and arrives in 2027, the calculated rate will be lower. The cosmologists will be right, forcing scientists to seriously question our current understanding of dark matter. This high-stakes waiting game is about to scale up. With powerful new ground surveys coming online shortly, spotting these specific lensed supernovae is going to shift from a rare stroke of luck to a routine scientific harvest. The deepest, most complex crisis in modern astronomy won't be settled by theorists rewriting equations on a chalkboard. It will be resolved by a looking up, and simply waiting for a dead star to show us the light.